This video is brought to you by mywayteaching.com.
In this part, let us study the limitations of dimensional analysis. In any dimensional formula containing MLT, we get at the most three equations by equating power of MLT. Hence, dimensional analysis cannot be used to derive the exact form of a physical relation if a physical quantity depends upon more than three physical quantities. Okay, usually in all the no the physical quantities, it will be depending on MLT. So it is very difficult to get the physical relation if a physical quantity depends upon more than three physical quantities. So that is the first limitation. The second limitation is information about dimensional constant cannot be obtained. For example, T is equal to K square root of L by G. Here K is a constant and the value of K is 2 pi, but this value we will not get using dimensional analysis, or the information about this constant K also we will not get in this dimensional analysis. By performing some other experiment, we will get the value of K as 2 pi. So this is another limitation of this dimensional analysis. And the third limitation is dimensional analysis cannot be used to derive relations involving trigonometrical, exponential, and logarithmic functions. Such functions are dimensionless. For example, in sine omega t, if I consider sine omega t, I'll not get any dimension for this. And even e raised to minus k functions, omega t, kx, are dimensionless respectively. In this, even e raised to minus kx, in both of these cases, omega t and kx are dimensionless. Okay. And the fourth important point is this method is not useful if a constant of proportionality is not dimensionless. For example, in equation like F is equal to G, the gravitational force m1 m2, F is equal to G m1 m2 by r square. Here the constant of proportionality, or the gravitational constant G, has a unit. It is not dimensionless. Its unit is Newton meter square per kg square. So such equations cannot be obtained by dimensional analysis. So these four are the limitations of this dimensional analysis. Now let us see one simple problem. The SI unit of energy is joule, that is equal to kg meter square s raised to minus 2, that is second raised to minus 2. That of speed of v is m s raised to minus 1, and of acceleration a is m s raised to minus 2. Which of the formulae for kinetic energy K given below can you rule out on the basis of dimensional arguments, where m stands for mass of the ball? So which of the following we can rule out on the basis of dimensional arguments? Every correct formula or equation must have the same dimensions on both sides. It should follow the homogeneity of equations, isn't it? And also, only quantities with the same physical dimensions can be added or subtracted. The dimensions of the quantity on the right hand side are m square L cube t raised to minus 3. For the first one, that is A, m L raised to 2 T raised to minus 2. The dimensions. And for B and D, it is m L T raised to minus 1. So for the first one, it is given by m square L3 T raised to minus 3. Isn't it? For the second as well as the fourth one, the D1, we'll get same dimensional formula, that is mlt raised to minus 2. M L raised to 2 and T raised to minus 2. And for the third one, we will get it as m L T raised to minus 2. The quantity on the right hand side, or E, has no proper dimensions since two quantities of different dimensions have been added, isn't it? One is this half mv square plus this ma. Since the kinetic energy K has the dimensions, this K is having the dimension, that is m L square T raised to minus 2. Formulas A, C, E are ruled out. Okay, because both the side it should have the same dimensions, but this is not having the same dimension as that of K, isn't it? So we can rule out A as well as E. It is the addition of two different yes, quantities with different physical dimensions. So this is also ruled out. Note that dimensional arguments cannot tell which one of the two, B or D, is the correct formula. For this, one must turn to the actual definition of kinetic energy. So using that, if we see, the correct formula for kinetic energy is given in B. Okay, even though dimensionally this is correct, but the formula, according to the theory explained in physics, it is half mv square, not 3 by 6 mv square. Okay, so the answer is B. Let us consider one more simple problem. Consider a simple pendulum having a bob attached to a string that oscillates under the action of the force of gravity. Suppose that the period of oscillation of the simple pendulum depends on its length, mass of the bob, and acceleration due to gravity. Derive the expression for its time period using the method of dimensions. Okay. Now we should consider a simple pendulum which is attached to a string, and even it oscillates under gravity, and even it is having the oscillation of that pendulum depends on length, mass, and acceleration due to gravity. So now we should derive the expression for its time period using the method of dimensions. So to what is the value, that is k L raised to x, g raised to y, and m raised to z. So where k is a dimensionless constant, x, y, and z are exponents. By considering dimensions on both the sides, we can write L raised to 0, m raised to 0, t raised to 1. And k is a dimensionless quantity, and L is the length 1, so raised to the power x. And for acceleration, we have L raised to 1, T raised to minus 2, that is raised to y. And for mass, it is m raised to z. So this one L raised to x and this one raised to y. So it is Lx plus y t minus 2y and m raised to z. And we have L raised to 0, m raised to 0, t raised to minus 1, isn't it? So equating these two, we have x plus y is equal to 0, isn't it? And minus 2y is equal to 1 and z is equal to 0. And therefore y is equal to minus 1 by 2. If y is equal to minus 1 by 2, what is the value of x? X minus 1 by 2 is equal to 0. Therefore, x is equal to 1 by 2. So now we can substitute it in k. T is equal to the time period k, L raised to x, that is 1 by 2, g raised to y, that is minus 1 by 2, and m raised to z, that is m raised to 0. Or we can write it as on another way, k is equal to square root of L by g. So these are the few examples of the derived physical quantities. So that the way we'll derive the dimensional equation. In this table, you can see some of the mechanical physical quantities where we have derived the dimensional equation for area, volume, velocity, and for various other physical quantities. And here also you can see the dimensional formula for energy, work, heat, torque, power, density, pressure, impulse, and inertia, luminous flux, illumination, entropy, volume, viscosity, dynamic viscosity,